Good morning. Can you hear me? All right. Okay. So today we will go into a new chapter. Okay. Continuing from the previous week, last 2 weeks we talked about the type of components that you may use, right? Okay. So today we will go into the more specific. Okay. Today we will go into the look into the shaft, right? So now in the shaft design itself, as you know, shaft is one of the important component, okay, that helps us to transmit power from one end to the other end, right? So before we start, all right, again, this time you may not need to put in your name and matrix number in the chat box, okay, but then I will provide you with the attendance link, okay, in the chat box during the Q&A or maybe towards the end of the talk or the sessions today, right? So again, just to remind you again, because we are doing it online, so it may be difficult if we have how to say, a long period of time, okay, in between, that you may forget about your work. All right, so as this slide just to show you and remind you about the type of assessment that you have. Okay, so we will try to have our first test, okay, to cover from the first lecture, okay, to the fifth lecture, okay. That will be before the design, okay, everything before the design components itself, okay, then it will be covered, okay. So it will take 10%, okay, out of the 30% given here, right? So make sure you register in the Google class. I saw there are still 2 names not there, right? So make sure you register in the Google class. So we will do it next week, okay, 12th June 8:30 a.m. right, in the Google Classroom, okay. And then at the same time I will give you more instructions, okay, from time to time, okay, how we will run the test, okay. So this test everyone must come at the same time, okay, 8:30 next week, okay. So if you have problem with the connections, everything, let me know before that, okay, so that we will try to adjust and see how we can proceed with that. All right, so okay, now back to the shaft story, right? So in the shaft itself, we can categorize them into 2 types, okay. The first type, the transmission shaft, and the second one is the machine shaft, okay. So what is the difference is that where they are applied, okay. So the transmission shaft itself basically is to transmit power from one energy source or the power source to the machine or to the other side. So we can see that the transmissions, okay, the transmissions shaft itself transfer power from the power source to the machine side, okay. Therefore it may carries a machine part like pulley, maybe pulley here, a pair of gears, all right, and other things, okay. Whereas the machine shaft itself is part of the machines, okay. So inside the machine itself there may exist a shaft, okay, to handle their functions, okay. They may need some kind of rotations and transmit that rotation to another part, okay, so that they are doing things in the synchronous way and other, right? So the name of the shaft, the general name is shaft, okay, but then there are some specific name, okay, such as axle, okay, you have heard about axle, car axle, okay. Then also the line shaft, okay, spindle, counter shaft, and jack shaft, okay. So they are given depending on the where they are applied, Okay, so for the axle itself, okay, as we know, okay, it is just a rotating part, okay, that connect two rotating element like wheels, okay, or maybe drums or maybe shaft. All right, so they should be a bearing supported, okay, so you may have a bearing, okay, to support your axle, okay, or general name shaft, okay, but in specific application is the axle. Okay, so when they are supported, then there will bending moment occurs on this axle itself. Okay, so the bending moments is due to the transverse load, okay, like the bearing reactions, okay, reactions of the bearing, okay, because the load may be over here, okay, and over here and over here, right? So it depends on how it is assigned. Okay, so the examples may be this rail axle of a railway wagons. Okay, so occasionally axle will also transmit torque. Okay, sometimes, for example, our cars rear axles, okay, where some cars they may power or move the car itself, okay, from the engine, okay, and it is connected to the back, okay, so that it will rotate, okay, the axle itself will rotate itself, okay, together. Okay, whereas another type of shaft will be the line shaft. Okay, so this line shaft usually in the productions factories or workshop, okay, where you have a group of drive, okay, you may see hanging at the top is the line shaft, okay, where they are connected to different machines, okay, the power source itself, so they are connected so that this line shaft may deliver some kind of rotations, and this rotations is transmit to the work, okay, or the machine itself. Okay, so again you can see that it is along the way, so that every machines that receive the rotations will be at the same or synchronous way. Okay, so it consists of a numbers of shaft which is connected in the axle directions by means of coupling, right? Then we have also spindle, okay, a short rotating shaft, okay, a short rotating shaft, we can call that as a spindle itself. Okay, usually is used in the lathe or drilling machines. Okay, if you have been in the mechanical workshop, okay, at the back of block B, okay, at the back of block B there you may see a lathe or drilling machines where they have a small rotating part, okay, that you may put your drill, okay, and so on. All right, so we may call this as a spindle, okay, a short shaft. Okay, then we have also a counter shaft, okay, which acts as a secondary shaft itself. So we have the main driving spindle, okay, and connect to the secondary, okay, which may connect to another machines. Okay, so we will call this as a secondary shaft or counter shaft. Okay, so it may be used in the multi-stage gearbox and other things, right? Then we have also a jack shaft. Okay, so for the jack shaft itself, it is an intermediate or auxiliary shaft itself, and it is used in the transmission power. Okay, so you may see that this is a top view of let's say this is a train itself. Okay, so the train itself consists of the two wheels. Okay, looking from the top, okay, you can see two wheels connected by an axle, right? So this jack shaft is here, okay, where it is an auxiliary, sometimes parallel or whatever. The purpose is to transmit the power, okay, to your rotating part, okay, to the axle itself, right? So you have the power source, the engine or whatever, okay, connected to the jack shaft. Okay, so the functions may be similar to the counter shaft as well. Okay, as a counterpart, okay, you may transmit from one power source to the counter shaft and distribute, okay, to the others, right? So before we move on to the design, okay, just general quick check, okay, what is the common cross section shape of a shaft, okay, how it would looks like over here, okay, if we cut this off, okay, so how, and you look at this, how the shaft will look like this in a circular or a rectangular. You may put in the chat box. Any ideas in your view, okay, that you have seen some shaft, okay, in your life? So what are the common shape that you can see? Circular or rectangular? A or B? Does the spindle type use circular? Okay. Right. Okay. Yeah, I guess yes. Okay, so some of you already got it. Okay, it should be in a circular, typically in circular, but then there are some non-circular type of shaft as well. All right, so why the shaft are usually in a circular form? It is because in the circular shaft itself, okay, it has more uniform stress distributions along the radius, okay, so this is the cross sections of the shaft, okay, the circular itself. So whatever force acting on it, okay, so twisting force or whatever, the distributions of the stress will be uniform when it goes along the radius, okay. So because of this, they would be, as a result, there will be no significant distortions along the cross sections, okay. Whereas if we use a rectangular, okay, if we do a twisting, okay, then usually twisting is a circular form, so the stress level will again in the circular form, so this part, okay, may be subjected to different kind of stress, okay, maybe lower stress, this one higher stress, okay, at this point. So there is a inconsistent stress acting on this kind of shaft, so there would be more distortions, okay, on this part, but not on this part, okay, so there will be a non-uniform kind of distortions and cause it to deform a bit, okay. So now we look into the constructions of the shaft itself, okay. So as we know, the shaft are commonly in circular in the cross-sectional area. It can be either solid, okay, a full circular form, or in the hollow, okay, a full circular form, or in a hollow, just like a pipe. All right, so the hollow type of shaft, they have the advantages of being lighter, okay, because you remove the material over here, okay, they are lighter, okay, and they also, because they are lighter, they produce more strength per kilogram of material, okay, if we compare in terms of the weight, okay. Also they allows internal support, meaning to say, if we use a circular type of shaft itself, okay, with the solid type, okay, you may want to support it, okay, then you may put a bearing, okay, a bearing outside, okay. Whereas if we use a circular one, then we will have options, okay, to add in the support, okay, internally, okay. You may want to put in some roller inside, okay. So this dotted line is the internal hollow, okay, so you may put some roller on this side, okay, on the other side as well, okay. So you allows some kind of internal support, okay, inside. So the suitability of the hollow shaft, as we say, is lightweight in constructions. Okay, minimum outer diameter shaft is now important, right? And also a hole of the minimum diameter is also important. The only problem if we use this kind of hollow shaft is how we construct, okay, this kind of hollow, right? How to construct this kind of hollow shaft itself, okay, and how we can maintain the shape of the shaft itself so that it will not go too thin on one side, okay, so that it's still able to transmit the kind of torque or functions as we want. All right, so examples, we have the propeller shaft, okay, and the main shaft between air compressor, okay, gas turbine, and so on, right? They are using hollow shaft because of the lightweight, okay, they are more concerned with the lightweight, okay. But generally, if we look into the machine in the workshop, okay, when the weight is not that critical, okay, you just put the machine static there, okay, and you will not cause extra fuel, okay, then they may use the type of the solid type of shaft, okay. It depends on the applications, right? So sometimes also we may need the kind of hollow shaft, okay, because internally you may want to put another shaft, okay, through it, okay, so that they can transmit two kind of rotations. For example, in the robotic arm, okay, you may have several axes. This one rotate here, this one rotate here, so they are controlled by different kind of shaft, okay. So if is needed, okay, some kind of the design, they may design different shaft, okay, but they are parallel, okay. So maybe one is at the outer and another one in the inner, right? So the type of material used for the shaft, usually we will select based on the material property, okay. So the property is important, okay, but generally we will use ductile material, okay. Ductile material means we are using steel, right? Various type of steel, okay. We don't use brittle material, right? Still there are some brittle shaft itself, okay, due to maybe the needs, okay, the aesthetic or other things, okay. But then generally we will use ductile material, and the material that we choose should be generally high strength, okay, good machinability. We can machine it, okay, to form different diameters, radius of the shaft, okay, at different sections. All right, then we have low notch sensitivity factor, which we will talk about later, about the stress concentration part, right? And then good heat treatment property. So after we machine it, usually we will do some kind of heat treatment to strengthen the outer side of the shaft so that it is stronger on the outside, so it can maybe become less sensitive to stain, less easy to be scratched, because it may increase the possibility of breaking down the shaft and so on. All right, so we may want to do some kind of heat treatment, okay. So ordinary shaft, we will use the carbon steel type, okay, that have a carbon content between 0.15 to 0.4%, right? So this the compositions, right? For example, this one is the coat itself, okay, for the ordinary carbon steel materials, right? For a greater strength shaft itself, we will use a high carbon steel. Again, in that we will add in more important elements, okay, into the material, okay. For example, chromium, nickel, monomium, okay, so to form alloy, right? And when it is in the alloy form, usually they are much higher in terms of the strength, and also they have the ability to resist rush, okay. So here usually the alloy steel are more costly than the plain carbon steel, okay. But then if we look into the possibility of getting a higher strength, hardness, toughness, and so on, then it may be worth, okay, depends on your applications, right, and the value of your machines or the design that you want to deliver, right. So also we will have a commonly commercial type of shaft, okay. So in the commercial type of shaft, it is usually a low carbon steel, okay. And in this low carbon steel, how we produce the shaft, it can be produced by either a hot rolling or cool rolling, okay. But usually or generally we will produce with the hot rolling, and then we finish with the cool drawing or turning or grinding, okay. Hot rolling, okay, because the cool drawing itself will produce a stronger shaft than the hot rolling itself, okay. So first we will see videos, okay, and how it may works, okay, in the let's see if we can load the video. Alright, I guess the video failed to load. Okay, never mind, I will share the link, okay, where I get this video from the YouTube. Okay, so generally what we would have during the hot rolling itself is that we have a roller, okay. So in order to produce a thinner or roll kind of shaft, okay, so we may have a hot, okay, we will heat the material itself hot, okay. So assuming this is red hot, okay, so now we will push this in between these two rollers. So when it get into this roller, it will be squeezed, okay, to a smaller form, okay, and being rolled, okay. So if we have, and also this roller itself, we may have a shape like this, okay, so that whenever it cut, okay, so it form this round shapes, okay, say similar to the bottom side, okay, we get a round shape. So indirectly we get a rolling type of a smaller diameter, okay, and a long shaft, okay, or material itself, okay. So when this is hot itself, as we mentioned, we may want to finish it with a cool drawing, okay. So after we get this long shaft, okay, we may further improve the material property of the shaft. We may do a cool drawing, okay, meaning to say we may again adjust another roller, but this time it's not hot, okay, it is in the room temperature, not exactly very cold, okay, but it's a room temperature. We call it as cool drawing. We will again push, or we can pull, okay, so that it being rolled, okay. So when it being rolled, the surface of this shaft will be getting better, right, because it's being compressed, okay, remove other things, okay. So sometimes if we want, we may also do a kind of finishing, like we grind it, okay, we do a turning means we are using a lathe machine, okay, to produce different kind of diameter or reduce the diameter of your original steel round bar that you have, right. So that is the general shaft, okay, hot rolling and finished by the cold drawing, turning, or grinding, okay. So turning is the lathe, using the lathe machines, all right. So we also see that cold roll shaft are stronger, right? Yes, okay, because they have when we do the kind of rolling itself, it will affect the crystallizations of the material, right? And when it recrystallize, then it may have different kind of property, okay. But then the cold roll itself may consist of a higher residual stress, okay, meaning the stress inside the material itself, okay? It's not being released outside, okay? It's acting inside, okay? Just like you have a metal and you hit it, okay? So the hit point now it deform inside, okay? So internally inside actually there is a stress inside, okay? But we don't see it, okay? It can't push it out, okay? So because of it cannot push it out, so everything is now inside, okay? So we call that as a residual stress, okay? So now we will talk about the force and power on transmission shaft, okay? Before that, maybe I will take some questions and see what kind of questions we have just now. Does the spindle type of shaft used in making the cordless drill? Yes. Yes. Okay. Does the car toy not sure this, okay? But then the car toys itself, you may see there are axle at the back, right? Very thin rod, okay? A circular rod at the back, okay, to support the wheel, okay? Two moving, two not moving, right? Or those not moving type, then you don't need the axle, okay? Those not moving type, four rolling wheels just attached to the toys car itself, right? And then what else we have? Circular chat delay. Yes. Does the car toy is example of countershaft? Internally in the car toy itself, you may have countershaft. Yes. Okay, I think no questions now. Okay, we will move on. Okay, so now we will look into what kind of forces actually acting, okay, when we try to transmit the power in the shaft. All right, so we look into the transmission shaft, okay, because this is more critical when it transmit power from one end to the other end. Okay, so you may have more power actually going through it, okay? But then once you know about this one, okay, so basically you would be able to design for other kind of machine shaft and so on, okay? So general ideas are the same, okay? So transmission shaft is a rotating machine elements, okay, that may transmit power from the gear, the pulley, or the sprocket. All right, so the application, yes, to transmit power, okay, and also to support the transmitted element, okay? So you may have transmitted elements like gears, okay? So in the shaft itself, we may have a maximum diameter at the middle portions and the minimum diameter at both ends, okay, generally, okay? Why we have this construction? Because we may want to support elements, okay? A shaft itself, it may be useless, okay, if we cannot able to add in the elements, okay? For example, here, let's say we may want to add a coupling, okay, from your motor, okay, the electric motor, okay? Then you may want to add in bearing, okay? So this bearing is a kind of elements, okay? So how we can support it? We will use this step, okay, to actually locate, okay, to fix the positions of this bearing, okay? So you may have a bearing here, okay? So this bearing will not able to move in further, right? So because of that, okay, sometimes you may also want another gears, okay? So you may have a gear here, okay, with a key to locate them, okay, to fix the to rotate the gear together. Okay, so this is a key slot. Okay, you have a key slot at the end also to connect to maybe another gear at the end. All right, so the shaft itself, besides transmitting power, it have to be supporting or locating the elements. Okay, so because of this, okay, we may want the design of the shaft in the kind of step. Okay, moving up to the peak. Okay, sometimes you may have one peak. Okay, usually we have only one peak. Okay, then we go down. Right, so the maximum diameter usually in the middle portion. Okay, some kind of shaft, yes, you can have at the end. Okay, like this, right? So why we need this? Because this elements or gear itself, they have a fixed diameter. So whenever you push it in, okay, you can only push in from one direction, right? So if we have a design of shaft like this, okay, so meaning to say some of the part actually cannot go in. Okay, if you have if we want to put in design, we may say, okay, we want to put in something over here. Okay, but how we slot in this thing inside? Okay, it will be blocked by these things, right? Okay, by this extruded part of the shaft. Okay, so that's why in generally we may want it minimum. Okay, so that we can slot the larger diameter here. Okay, then we slot in the bearing. Okay, then we slot another things over here. Okay, and then another part over here, right? So that we can put or assemble it. Okay, and the elements itself, the gears or bearings or whatever, it will be located, it will be fixed at these positions. Okay, so we will go through examples directly, okay, to illustrate better. Okay, so determine the bending moment and the shear diagram for a shaft below. Okay, so in general, when we start to design for a shaft, okay, these two things is important. Okay, I'm not sure whether you have learned about bending moment and shear. I guess if you have taken the applied mechanics course, you should have some idea of this. All right, so now these ideas will be applied, okay, for your design. Okay, so how it will be used? Okay, now we have a shaft. Okay, and this shaft will have a gear A, bearing B, gear C, bearing D. All right, for example, like this. Okay, so bearing the gear A itself now connect to another gear. Okay, and gear C itself connect to another gear, right? So when there is a connections, there will be a kind of reaction force given to by this gear to the gear A, right? So that kind of reaction forces, okay, or the power being transmitted, okay, would be resolved, or we will say represented by the WT, the tangential force, and the WR, okay, the radial force acting on gear A. Okay, so we have the A substrate, okay, to denote A. All right, same thing for the C. All right, so if we want to draw the bending moment and the shear diagrams, we may want to see a different angle. Okay, since we have forces in the radial form and the tangential form, so first we may want to just illustrate how we can draw a bending moment along this blue plane. Okay, so if we cut it horizontally, okay, this blue plane, okay, so we will form this simple free body diagram. Okay, so we just represent the shaft with a straight line. Okay, the straight line itself, okay, from point A to point D. This extra part we don't include because no force actually acting on that, right? Okay, and it useless to add in, so we don't put in that that sections, right? So we start from point A to the bearing D itself. Okay, so at point A we will see that there is a WRA acting. Okay, so if we rotate it, okay, this is the X, okay, and along here is the Z. Okay, so if you rotate your head, okay, then you will be looking like this, right? So moving these directions, going down, moving these directions, going up, right? And then because of that, we just, because these two usually we can predict, okay, the kind of force from the, we can calculate based on the torque or the power transmit from your electrical motor or engine. Okay, so from there we assume now we know it. Okay, it would be WRA is 3398, okay, whereas the WRC is the 6800 Newton. Okay, so we would want to know what is the reaction force being handled by the bearing B and D, right? Okay, so we can just draw two arrow as you like, okay, whether up or down, okay, and find this unknown RBX or an RDX. Okay, so how we can do that? Okay, we just use the simple principle, summations of moment equals to 0 and summations of force equals to 0. Okay, so you may want to take moment at point A, right? So if we take moment at point A, then this RB will give us this 254 multiplied by RBX, okay, in the positive directions, okay, because this contribute to these rotations. Then similarly, this WRC 6800 contribute to this direction, so again it will be positive 259 plus 318, okay, to get this length, multiply by WRC. Okay, and then this last part, this is counter part. Okay, so we minus this whole length, multiply by RDX. Okay, and we equate it with 0. Okay, so we will have the summations of moment at point A, let's say, okay, equals to 0. Okay, then we have one equation, and we can also form the second equation. Total forces should be equals to 0. Okay, so we have WRA plus RDX minus WRC minus RBX, okay, equals to 0. So solve them simultaneously, we will get the reaction force for these two unknown, right? So now once we have this reaction forces, okay, what we can do is we will draw the shear force diagram and the bending moment diagram. Okay, so the shear force diagram is just the summations of the force acting that cut through the shaft. Okay, so we will say that as a shear, right? So now we will just add 3398, okay, going down, so it will have the shear in these directions, right? So going down and along this bar, okay, it is maintained, okay, because no additional shear force downwards. Okay, but then at RB, when at point B, we will have this support 1887 that we get just now. Okay, so it will increase back. Okay, then again along this part, this segment, no changes of the shear force, and then we add in additional 6800 at point C. Okay, up again from minus 1511. Okay, at this value we get this one. Okay, and maintain, and you realize that this value and this value is the same. Okay, so that it comes back to 0. So no shear at the end of the shaft itself, right? Only the shear the direction of the shear and the magnitude of the shear differ across the shaft. All right, so also we can calculate the bending moment. So bending moment we will calculate based on the value. Okay, just like the moment, we will have a force multiplied by distance. Okay, so this value multiplied by this value, okay, we get this. Okay, this is in meter, this is in mm. Just convert them, that's why you get a small number here, right? So you multiply them, you get this number. Okay, so this, because of this rotations itself, it is slowly increase. Okay, as it getting further, the moment increase, right? So that's why we draw from 0 until this point. Okay, then same thing at this point, it rotates. Okay, then we have to add the effect of the bending before it come back again. If we want to see the bending at this point, okay, you can calculate for this. Okay, so it would give you this value. Okay, and eventually it comes back to 0 again, right? So this is how you can get the bending shear force diagram and the bending moment diagram, right? So same thing, you can do it for the vertical plane, right? That includes the WTA and the WTC. Okay, same methods. Okay, only different values of the WTA, WTC give you different profile, right? So same diagram. Okay, now both are moving downwards. Okay, moving downwards. Okay, then we have to support from the bottom, right? So you can try this on your own, right? So now how we use that information for our shaft design. Okay, so in the shaft design itself, you can see that we have the shear as well as the bending. Okay, so in general, the shear itself give us a kind of a different kind of load, but then generally the shaft will be subjected to the tension. Okay, if we pull it. Okay, but very rare we pull the shaft in this way. Okay, so generally we will have a bending and the torsion. Okay, so this shaft, when we support it, okay, so it tend to bend, and also there is a torsion because we rotate it. Okay, so it's a twisting. Okay, in the shaft itself. So the bending stress itself, if it is bend in this way, okay, when this shaft rotate, this part, the upper part which is bent down previously, when it rotates, this part will now move downwards, right? And the other side. Okay, so when it moves downward, then instead of bending downward, it being compressed, now at the bottom side it being stretched. Okay, so the load itself is being completely reversed and repeated. Okay, we will say that the bending stress when in the shaft itself, it will be subjected to a completely reversed and repeated. Okay, from being compressed at the top, okay, rotate down, being stretched at the bottom, okay, and rotate back, being compressed, and it keep rotating. Okay, so the bending stress change. Okay, so in the shaft, then the fatigue loading is more critical in sometimes. Okay, so fatigue refer to just like the type of the words you heard, stress. Okay, then you have fatigue. So when we talk about fatigue, it means when we apply it for a very long time. Okay, you may have a load, okay, or a piece of plastic. Okay, if you keep flipping it, okay, then it will start to break. Okay, we will say that there is a fatigue loading. Okay, if it is holding in one side, okay, it may not break easily. All right, it may still able to sustain. But if you just flip like this, up down, very little, okay, then slowly that part will start to have a more severe damage, and eventually it will fail. We will call that due to fatigue. Right, so in designs applications, we may put in different design factors. Okay, if it is not moving, just static loading, okay, we may put just 0.125 to 2. Okay, then also in some cases we may have a dynamic loading, means the load itself is not fixed. Okay, it may be changing from 1000 Newton to 2000 Newton to 3000 and then come back. Okay, so the loading is itself change. We may show that as a dynamic loading. Okay, then if we are not certain, so this again completed reverse and repeated load, because it changed from negative to positive, we may say that as a dynamic loading. Okay, a kind of dynamic loading as well, even though the value is the same, from negative 2000 Newton to positive 2000 Newton, right? For the conditions where we have uncertainty about the load, we are not too sure about the load, material and environment, then we may put higher factors. Okay, so in general, as we say, is the shaft may be subjected to three kind of force: the tensile load, okay, being pulled. So if we being pulled, the stress for due to the tensile is the load, the P divided by the cross-sectional area, right? You cut it and we get the area. Okay, force over area. Okay, then when we look into the shaft, that purely due to the bending moment, then we can calculate the stress due to the bending, given by the formula my over I. This m is the bending moment. Okay, so if we have the bending diagram, okay, just now we draw a bending diagram, something like this. So this moment is this value, okay, and it keep changing. So we will know the stress along the shaft, okay, it changed due to this changing bending moment value, right? Then also the shaft, when it's subjected to pure torsional means we twist it, okay, then the torsional stress will be the torque, the torsional moment, the torque itself multiplied by R divided by the polar moment of inertia, right? So three general equations to determine the stress due to three different conditions. Okay, so in the shaft design, as we have mentioned, it may be bent. Okay, the shaft itself may be bent. All right, so let's say this is inverted bend. Okay, it bend upwards. Okay, so there is a moment pulling this. So whenever it bend upwards, the top surface of the shaft is now being stretched. Okay, because it bend outwards, so it's being stretched upside. Okay, whereas at the bottom of the shaft is being pushed inside, being compressed. Okay, so if we look into the one segment or one small part, okay, on the shaft itself, okay, on the top, at the bottom, at the side, okay, the blue color. So you will see that at the top, if we cut this blue color, it is subjected to the bending stress, okay, being pulled out, okay, the easiest one, okay, and then because of the twisting, you can see the top twist it, okay, so this small rectangle at the top now being twist, okay, subjected to this. Okay, so we will draw it in this way. So this square itself, when it under this stress, it may now become like this, okay, being stretched, right? So this is the conditions. When it come to this side, now at this middle part, there will be no tension or compressions acting. Then in that case, it is purely due to the torsional. So the shape may just look like this, okay, same shape, may just turn, twist, okay. Whereas when it is compressed, again, when it is compressed, then it may be smaller like this, okay. So this is the ideal conditions where when we zoom into this particular part, we can see actually this thing is take place, okay. And how to calculate this stress, it is based on the previous equations, right? And that is how we can determine what is actually happened, okay, at that particular. So we can always combine them together using what we call a Mohr circle principles. Okay, we combine them together. So I guess this may not that important for you. Okay, so we will just quickly get through the idea. This is just a Mohr circle developed by famous Mr. Mohr, right? Okay, so we will identify the center of the Mohr circle itself, okay, and then we will draw a circle, okay, and from that circle we will know what kind of torsional stress and the other stress, okay, combined together, okay, when it is changing, right? So this is the formula from the Mohr circle itself, okay, just for knowledge, right? So I will not go through in detail for that. Okay, so now when we look into the fatigue loading, as I have mentioned, fatigue is about repeating load itself. Okay, so what is important now here is that we know about the tensile strength or the yield strength. Okay, so generally steel itself, okay, a ductile material, it will elastic, okay, and then it will become non-elastic before it fractured or being break into two parts. Okay, so this elastic part, okay, just like a spring, okay, you can pull it, come back to the original shapes. Okay, so this is the yield strength. Okay, when it reached the maximum, then this is the ultimate strength. So what happened in between this segment is that when we pull it, okay, and we release the load, it will not come back to the original state. Okay, so it will still able to sustain a kind of load, okay, until a maximum we call it ultimate strength, right? So here for the static, the similar type of descriptions, we for the fatigue loading itself, we will look into what we call a fatigue property, okay, or fatigue limit, okay, how many cycle it can do. Okay, so in general, the steel have this characteristics of fatigue. As the numbers of repetitions increase, okay, then the tendency for the steel to fail due to distress, okay, will also be maintained. Okay, so if let's how we will interpret this one. Okay, so let's say you have applications to rotate 10 to the power of 5 time, okay, and you do it at a load or the stress of 40 kilo square inch, okay, kilo KSI. Okay, so at this stage, this steel can sustain for this number of cycle. Okay, but you can also, if we try to increase it, then it may start to fail. Okay, it may not able to sustain that long. Okay, so if we want to sustain this kind of load, okay, it can only sustain around 10,000 times, right? 10 to the power 4. Okay, so we will see that as the cycle increase, then there is a limit. Okay, we call this as endurance limit or the fatigue limit. Okay, so we will see that the steel now, no matter how many times you increase, it can only sustain up to the 30 KSI. Okay, so it's the idea of there is a fatigue load. Okay, for the material itself. Okay, so we denote this value as the SN. Okay, so what we can do is, in actual, this is in the laboratory results. Okay, so in actual, we would want to estimate in the actual form. Okay, we may have some kind of reliability factors comes in. Okay, the kind of stress acting on the application itself. Okay, we put in the loadings. Okay, the size factors, the materials factor, and so on. Okay, multiply, so we will estimate a endurance limit for that. Okay, so if we want to get this value, we can always refer to internet, or some design book where they have a material properties, okay, for example these materials or in papers, okay, will able to sustain these numbers of how say megapascal, okay, around this value, okay, to sustain under this kind of a number of cycle. Okay, so now how we would use that, okay, we would use that estimated fatigue loading or fatigue limit, okay, in our design. Okay, so in general for shaft, okay, what you need to know is they may undergo two kind of condition. One condition generally, okay, there will be a bending stress, okay, in the shaft, and the torsional shear itself is uniform, meaning it is rotating by a given uniform power being transmit along, okay, but then there is a bending stress is in the shaft itself, okay, which is being repeated and reversed. Okay, so here in order to design for the shaft, this D represent the diameter of the shaft, okay, the minimum diameter of the shaft, okay, based on the theory itself, okay, of the material. So this diameter itself can be determined, okay, the diameter of the shaft can be determined by these equations, okay, 32n, this n is the design factor, divided by pi, okay, multiplied by the square root of kt is the stress concentration factors, okay, m is the bending moment, okay, that you have, the Sn we already know, this T is the torsions, okay, the Sy is the yield strength of the material itself. Okay, when we have this condition, we will use these equations, okay, to know what is the suitable diameter, okay, the minimum diameter that it can work, okay, to transmit that kind of power and bending moment, right? Whereas for another condition where there would be no torque and bending moment, okay, or it can be very low, but then there is a very high shear force, then in this case we will only take into account the shear force, the V itself, okay, the other parameters is the same, right? Again, we can identify what is the suitable diameter for the shaft. Okay, so we just go into the stress concentrations. Okay, what is stress concentration? Stress concentration is what happen in a shaft or a dimension. So whenever there is a changes of geometry, okay, so there would be a stress being squeezed in. Okay, if we draw the a flow line itself, okay, so everything will be squeezed into this corner, right? So there would be, we would say this is where the stress is being concentrated. Okay, this is due to the changes of geometries. Okay, also there will be stress concentration due to the key seat. Okay, when we cut a key slot over here, we cut a groove over here, so the flow is now being disturbed. Okay, and you have to come over here. Okay, because when we cut it off, whatever tension or compressions occurs on this surface is now cannot being transmit from this surface to the other. Okay, it have to go internally. That's why it will cause some kind of stress concentration around that changes of the geometry. Okay, so generally we will just cater for this by assigning concentration factors. Okay, so for key seat, okay, when we put a key here, then we will put these factors. Okay, for a shoulder, we will say this is a shoulder, the step itself. Okay, step. Okay, there is a step, a shoulder. Then again, these values, okay, different. This depends on it is whether it is sharp or round. All right. Then also we will want to put in a ring, okay, to fix the locations. Then we may cut a groove, okay, on the shaft itself. Okay, then in that case we will put 3, okay, a very high stress concentration factors. Okay, so now come back how we could apply to our previous problem, right? So in this case, let's say the gear A will receive 150 kilowatt. Okay, then gear C deliver the power that you receive from gear A to gear C, and the shaft is rotating at this particular speed. What we can do is, since everything is constant, okay, not much changes in the load, we know many of the information, we will take the design factors as 2. Okay, the dynamic loading, the lowest one. All right, then from there we will compute the torque being transmit. Okay, to calculate the torque, it is equals to power divided by the speed. Okay, we would get this value, the kind of torque being transmitted. All right, so this value divided by this value, right? Then also now we would want to guess, okay, what is the size, suitable size for this shaft. Okay, if we are using this material, okay, so from this material, okay, we estimated or we get it from test or some data book. Okay, what is the property for this? Okay, so we will have the yield strength, ultimate strength, and the estimated fatigue limit, okay, as given as such. All right, so now when we come to design, we don't know the diameter. Okay, all this diameter is unknown. Okay, so what we do, we will just put in this segment, okay, where we would put some part A is the gear S. Okay, so here we would put our gear here. Okay, but then what is the size of this shaft? Okay, we put D1, then D2, D3, D4, D5, D6. Okay, we just want to calculate what is the minimum diameter along the shaft. Okay, you may cut into more segment, up to you. All right, as long as we can cater for important changes of geometry. There is a key slot here, there is a fillet or shoulder here, there is a shoulder here, there is a key slot here, there is another shoulder here, there is a ring groove here. Okay, so we have 1, 2, 3, 4, 5, 6. Okay, 6 segment that we want to locate. Okay, so based on that 6 segment, we just go through the stress concentration that would happen at that particular locations. Okay, so at that particular locations, A and C itself is a key slot. Okay, key slot, sled runner key slot, we have a KT 1.6. okay, then for the D2 and D6, since we have larger dimension, we would put a round fillet over here. Okay, then that is 1.5. but then D3, because this is very minute, okay, we may have problem to machine this. Okay, and also we may want to put some things here. Okay, that is the reason we may have to come up with the sharp fillet there. Okay, so we have 1.5, 2.5, and then there is a retaining ring over here. Okay, so it's 3. Okay, so based on that KT at different locations, now we will use it to calculate. All right, so now remember, previously we obtained this bending moment. Okay, if you do it for the vertical plane, okay, you will get this bending moment as well. Okay, so we will see that the bending moment diagram itself change, okay, the respective to the locations. Okay, so here we would combine the moment acting at one particular point or location. So if we take this point B itself, then we will take this value and this value. Okay, we square them and take a square root. Okay, to find the resultant moment acting at the point B or location B itself. Okay, so if we calculate, then this is what we get. Okay, 0 at both ends, and there is a resultant moment, okay, at B and C. Alright, so once we have all this information, we just apply our equations depending on the situations. Okay, so for point A itself, generally it is due to the bending itself. Okay, for point A, so we will use these long equations, and in this equation itself, and we know that at point A there is no bending moment, right? At point A there is no bending moment, so this term disappeared. It's purely due to the tension itself. So whatever stress is due to tension, this will determine our diameter for point A. Okay, so you just put in all the parameters, okay, values here, you will get D1, right? Then same thing for point B. Okay, so at point B we have two segments, the D2 and the D3. Okay, so come back again, D2 and D3. Okay, point B we have this fillet, we have this fillet, right? So what we do, same thing, same equations, we just put it in at that particular point, we will get the value for D2 and D3, right? Same thing for point C. Point C we have the highest point with a groove. Okay, so this is where we have the groove part. No, this is where we have the groove part, I guess. Okay, so you just put in all the parameters, okay, at that particular positions, we will get the respective diameter, right? And lastly, at point D, when point D itself towards the end where there is no load. Okay, so if you check again, what I mean by no load means you can see the torsional force. Okay, it is being transmitted from gear A to gear C, so the torsion or the torque is being transmitted from point A to point C. Okay, so after point C, no torque being transmitted towards the end, right? So that's why at point D itself is purely due to the shear force. Okay, and because of that we will use this equation mainly due to the shear, and we will estimate the diameter at point D6, right? So now we have D1 until D6 at different locations. Okay, so how we can determine the actual diameter that we would want to use. Okay, so since we have a general idea that D1 must be smaller than D2, D3, and D2, D3 must be same. Okay, then D4 and D5 should be same, right? Okay, because this is the same segment. Okay, and this D6 should be smaller than this. Okay, this is greater than this. So from here you just check D1, you may select any values that satisfy D2 greater than D1 and also greater than the minimum required diameter. Okay, then for DB, the part B itself, they must be equal, so just choose between these two which one more suitable for you. Okay, this value is minimum, so whenever, let's say this D2 we get 2 millimeter and this we get 3, which one should we use for DB? We should get the higher one, right? Okay, so that it satisfy both conditions. Okay, so we will select DB. Okay, so this D1, let's say this is 1, so if we choose 3 here, we choose 1 here, this one is still greater than this one, so this condition satisfy, right? So this is how we will select it after we get the minimum required diameter across the shaft itself, right? So that is the procedure or the methods that how we can design for a shaft. Okay, so generally we would want to know the speed, the power, the locations of where we would transmit. Okay, general descriptions. Okay, where we want to put the bearings. Okay, the geometry, some idea of the geometry, where is the highest, the lowest, maybe where you want to put the key. Okay, and so on. Then what type of torque, the magnitude of the torque, okay, the force exerts, okay, the reaction force. Okay, from there you can calculate the direction force. From there again we generate the shear force and bending moment diagram, and now we select the material. Okay, after we select the material, now we will come to the calculation part. Okay, that we have demonstrated previously. We select the what kind of conditions we apply. Okay, from there we will check which is the critical regions that we want to know the minimum diameter. Okay, so from there we will calculate, and at the end we will finalize the dimensions. Okay, so this is what we generally do to design a shaft, right? So that's all for these sections. Any questions or anyone want to talk? Let's wait. Okay, so while waiting for questions, I will post the attendance link now. Okay, so you can use this link to mark your attendance for this sessions. Okay, so I guess if we don't have questions now, okay, we will end the sessions. If you have questions, you can always ask in the Google Classroom. Okay, it's free to talk, right? Don't worry. No questions? For our test later, will there be questions just like the calculation shown? That will be in the test 2, not this coming test. Okay, it will be in the test 2. So in the test 2, yes, some basic calculations, okay, not in that detail because that will take a long time. All right, so I will know maybe the basic equations, maybe to calculate the bending moment at that one particular point, or maybe finding the reaction force, or maybe use one of the equation with all the parameter given for you. Okay, that may okay, but maybe 1 or 2 question, not more, not much. Okay, so any more? Yes. Okay, I think if no more questions, anyone want to talk? If no, we will end the sessions. Yes. How long it would take, because 9:30 we have a test for another subject. That one we will try to finish in half an hour. Okay, so 8:30 we will try to start. Okay, if no technical problem, right? So if there is some technical problem, there will be some delay, but then hopefully in half an hour it will not affect your second test. All right. No more question? Okay. Okay, so I hope that's all for today. We will see you again next week. All right. Okay. See you.